Okay.
Okay, so I got interested in this topic because I had several images in the last couple of months that have been really excited about the data, but it had this weird gradient or anomaly after calibration that I just really couldn't get rid of effectively. I've stretched this one far too much to kind of accentuate it, but you can see this arc on the left side of the image. Might not come across Zoom very well, but trust me, there's an arc on the left side, and then there's this arc on the right side. So in addition to having a gradient, there's this halo, an area where it's kind of brighter, and there's a trough, and it gets brighter again. And about a year ago, I started noticing it just in my focus images, and then it would kind of go away. So I assumed it was frost, and then in the last 3 months, it's become a common issue, and it takes longer and longer to go away, and it's messed up enough images. I thought I need to do something about it. And obviously what's happening is I'm getting condensation inside the camera chip chamber, because as it cools down, the water's condensing out, which is a classic sign that the desiccant inside the chamber needs to be recharged. So I thought I would drone on a bit about desiccants, and I found the whole thing kind of interesting as I dug into it. So all desiccants are similar. They're hygroscopic materials, so they're absorbing water and intended to reduce the water vapor inside the chamber of a sealed camera. The two most common types for a camera are silica gel and molecular sieves. So silica gel, we all know, little glass beads, and a molecular sieve is similar, but it's a synthetic material that is far more aggressive at pulling moisture out of the air. There's some less common ones that I've seen over the years, but almost never see them anymore. One's activated charcoal. It acts as a desiccant. And then there's these deliquescent salts that they're really just types of salt that tend to absorb water, and then they become a liquid. They're not used in cameras, but I see them occasionally in specialty applications. And they all have the same operating principle, particularly the silica gel and the molecular sieves. They have these tiny little pores. They're using capillary action, or the intermolecular forces between water and the desiccant material to pull in water or hold moisture once it's in there. So again, silica gel is the most common. We see it in all kinds of packages. It's been known for hundreds of years. It became very popular in manufacturing settings in the 1940s as electronics were being shipped around the world because of World War II. The silica gel prevented condensation in the packaging. It's got a very fine porous. It's silicon dioxide, so therefore very hard, withstands temperatures quite well. It's whitish, and it has these very, very fine, that's a typo, it's actually 1 to 3 nanometers, not millimeters. Oh, no, that is right. 1 to 3 millimeters in diameter, and the pore sizes are quite small, 2 to 7 nanometers. So you can see that capillary action goes up as the square, or go down, it goes up as the radius goes down by the square. So this small of pores has really strong intermolecular forces that pull water vapor in, or once it's in there, it keeps it there, particularly water droplets, liquid form. Chemically inert, non-toxic. And the silica gel is there really to prevent condensation. It doesn't reduce the humidity a lot, or not in the long run. Once it's freshly recharged, it will certainly reduce humidity, but that's not the real value of it. The real value is that if the temperature drops near the dew point and you're starting to get condensation, particularly in like a plastic bag or an enclosure, that condensation immediately gets pulled into the silica gel and has the effect of temporarily reducing the humidity, so you don't get condensation all over the inside of the container. And once the temperature warms up again, it'll release it. So it's not a permanent capture of water. It'll release it or absorb it. But the big value is once stuff gets near the dew point, things are starting to condense, then the Silica Gel is attracting that water vapor and holding it. And these are easily recharged. You put them in an oven for a couple of hours and just warm it. 200 degrees Fahrenheit is what I usually see. And they'll dry out. It bakes out the water. It does take some time because it holds on to water so well that you need to leave it in there again for a couple hours, and the water will be baked out, and then you can put it in a airtight or watertight container to keep it fresh. There's also color indicating gels that will turn colors. That the value of these is they tell you if they're saturated. So in this case, blue is a saturated material, and it's just telling you need to bake it out. These are kind of nice. I don't see them as much as I used to, partly because they're kind of expensive. Actually, I should say, I put this image here, Multisorb. United States is one of the largest producers of silica gel, and this company, Multisorb, is it's a sister company to the company I work for, and they make these silica gel packets in very high volume. The other kind, and the kind that we see in our CCD and CMOS cooled cameras, is a different material. It's a different material enough that it has a completely different name, and they're called molecular sieves. They're very aggressive and powerful desiccants. Mostly they're made out of zeolites or aluminosilicates. So it's where aluminum oxides with some other metal oxides, but alumino oxides or aluminosilicates have some interesting characteristics. They're very strong, durable, very stable. They withstand temperature changes very well, and they're long-term stable. They don't have chemical reactions, but you can also make very, very fine pores throughout this material and mold it into these different shapes, including plugs like you see in the top image. It's similar to what's put in our cameras, are usually molecular sieve plugs. And because of their nature of having this porosity and a very fine porosity, they actually pull down humidity. So they're not just reducing condensation, but they're drawing in the water vapor. And they can draw in as much as 99% of the vapor out of the air. So it's really quite aggressive way to reduce humidity. And they can also be recharged, but they require a lot more aggressive recharging. And that is, you have to bake, at least mine, I have to bake it for 4 hours at 500 degrees Fahrenheit. So those are the two main types, the silica gel and this. Now, I'm going to go off on a bit of a tangent about dew point, because it's really important, at least for me, it was really important to think about dew point to understand what these desiccants are doing in our chambers and why my image is getting foggy with it. So dew point is the temperature, of course, at which air becomes saturated, or it has a 100% relative humidity. And at that point, condensation begins. The dew point is often referred to as a measure of absolute humidity because it's related to the total grams per cc of water in the air. It really determines the dew point, and the easiest way to think about it is the dew point. Relative humidity, of course, is just the moisture in the air relative to the maximum amount that air could hold at that temperature. And I'll go through some examples in a minute that make that a little more clear. But relative humidity changes with temperature, but the dew point does not. So if you're on an observing night and it's 50% humidity and maybe 20 C, and as the night goes on, the temperature drops maybe to 15 C, and the humidity will go up, and you think, wow, it's getting more and more humid. But really what's happening is the temperature is approaching the dew point. The air can't hold the humidity as well, so the relative humidity is going up. But the absolute humidity, the total amount of moisture in the air usually doesn't change over the course of a night, which is why the dew point's a good way to measure seeing, because the lower the dew point, the lower the total moisture in the air. And this is really an important point. and considering what desiccant to use for a sealed camera and what will work and won't work. There's a formula here I just got from Wikipedia if you ever want to calculate. I didn't use the best formula, but if you ever want to calculate the dew point from temperature and humidity, it's pretty straightforward. So doing that, let's look at one simple example. Why is the air so dry in winter when you're inside? So if it's 5 degrees C outside with a relative humidity of 70%, then the dew point is 0 degrees C. Now that air comes into the house, you open the door, this parcel of air at 70% humidity, 5 degrees C, comes in the house and it gets warmed up. So it starts to warm up to 10 degrees C. Well, the relative humidity will drop because the dew point isn't going to change. The total amount of moisture in the air hasn't changed. It's just the relative humidity, its ability to carry the moisture has changed. So the relative humidity will go down, the temperature goes up. And then finally, if it goes up to 20 degrees C, the relative humidity will be 6, and the dew point will stay at 0. So it's always kind of fun when I have a dew point meter. I can go in and out of the house, and you see the temperature and humidity going up, the other one going down, and the dew point doesn't change at all. So yeah, as the outside air is warming, it comes inside. It's got more carrying ability. Now it doesn't work in reverse in the AC. With the AC on in the summer, it's very different. The AC is actually removing moisture, goes down the drain from the condenser. So it's lowering the absolute humidity. It's lowering the dew point, but it behaves a little bit differently. So back to cameras. Now what's the point? The point is, if you really want to get the inside of a camera chamber cold without it fogging over, the sensor cavity must stay very dry. It was surprising to me when I started reading about what a molecular sieve needs to do for our cameras. So on this upper table, I just want to use the example of a little bit repetitious, but if I'm at 20 degrees C, 70% humidity, and as the temperature goes up, the relative humidity will go down, the dew point stays the same. If I, on the bottom table, now think about a camera body, I start my camera off at the beginning of the observing night, it's at 20 degrees C. If I don't have a desiccant and I just had an open air chamber that I can now close that chamber, that's got air in it, it's going to be at ambient relative humidity, let's say it's 70% because it's Missouri and it's so humid. The dew point of that amount of air is 14.4 degrees C. Right, so this is really important. It's 20 degrees C air, 70% humidity, so just ambient air. If that were to be in the camera, its dew point is 14.4. What that means is if I cool my camera down to 14.4 degrees C or lower, that the water is going to condense out onto the image window, the chip, the electronics, and everything else. But obviously, that's no good. So let's say you put in a desiccant, and let's say you put in silica gel. I closed that, I put in some freshly recharged silica gel, stick it in there. Well, silica gel doesn't really lower the humidity a whole lot. It's more about condensation. But let's just say I'm lucky, I get it down to a relative humidity from 70% to 30%. Again, I cool it down. My dew point's now at 2C. So at 2C, if I try to cool down to 0, again, got water all over the chamber, water on the chip, water on the window, frost on the window. So that's no good. The advantage of a molecular sieve is it's pulling down most or almost all of that moisture. But even if I have 5%, so I've got a weak sieve, one that's near the end of its life, needs to be recharged, and I can pull that relative humidity down to 5%. Now look at my situation. My dew point's at -20. I can pretty safely get down to 0 cooling, or I usually go to -15. But at -20, I start getting that condensation. So a molecular sieve will often, I see claims that it will reduce the internal humidity to 1%. And that's what allows you to get cold. So you can see why, maybe obvious to you, but it took me a while to think about this, is it's really important to have a good charged molecular sieve, keeping the chamber humidity very, very low, because as you cool that camera down to -20, even a small amount of humidity can cause condensation or frost on a window, and it can mess up the chip, the electronics, and just not, obviously your image. So that was an important takeaway, and explained why, as my sieve got worse, my cooling temperatures started to show problems at higher and higher temperatures. I also found that the rate of cooling can affect condensation. It took me a while, again, to think about this, but it makes sense in hindsight. So if you cool really fast, you can increase the relative humidity faster than the desiccant can remove the water vapor. If I'm starting off, again, this is, I guess, it gets a little confusing, so I'm going to look at this a little bit differently. Before I was talking about the properties of the ambient air and what the dew point was. Now I'm going to hold the dew point constant and drop the temperature as the camera cools the chip. So I start off the night with my camera. I've got my molecular sieve is in shape, and it's keeping the humidity to 5%, and I start my cooling operation. Well, I start with a dew point of -20, so my temperature is at +20. I'm way far away from a condensation, so no problem. I cool down to 0. Well, now that parcel of air that started off at 5.4% relative humidity is now at 20% relative humidity. Still no problem. I'm way above the dew point. I'm not going to have condensation. But you see what's happening here is my sieve was able to pull it down to 5%, but now it's gone up to 20%. If I keep going to the dew point -20 cooling, I'm now at 100% relative humidity, and I've got condensation on my window or on my chip. Well, if I wait a little bit, the sieve, even though it's kind of weak, because I'm just kind of simulating an older one that needs recharge like mine did, well, I'm here at 100% relative humidity. Even a weak sieve is going to start pulling that down. So over time, as you see on the right, I'm going to hold my temperature constant, but that sieve is slowly pulling that moisture back out. And 10 minutes later, I may have 90% relative humidity. Maybe 30 minutes later, an hour later, I've got 50% relative humidity. And now my dew point's gone down to -27, even I'm at -20, and that frost starts to clear up. So if you do this really, really fast, even with a good desiccant, if you're cooling it at a rate that's faster than the sieve can pick up the moisture, you may get a transient fog on your window or on your chip. And that's how I first knew that I was having a problem. Was I was in a rush. I set it to 100% maximum cooling rate, and that's when I started seeing effects. If I let the camera warm up a bit and started cooling down again, but did it more slowly, I didn't see the problem. Or I'd cool it down really fast, I'd see the problem, and then I'd wait a little bit and the problem went away. And so what's happening here again is you cool it down really fast, the humidity jumps up, even if it was really low to begin with, and then the sieve kicks in over time, it's pulling that humidity back out. So one of the lessons to me, at least with my camera, was I have it to cool from ambient to -15°C in 5 minutes. So I let it just slowly get there while I do other things. I don't cool at maximum power. I was also reading about gas purging and read a lot of online and from what the manufacturer had to say. And this really surprised me a bit. But first of all, people think sometimes that gas purging also removes moisture. Well, it's not a desiccant. It displaces moisture if you put in dry gas, but it's not a desiccant. And dry nitrogen is probably the most common used in optics. It's inert, it's inexpensive and effective. What are used in some of our astronomy cameras is an argon gas, and it has a couple of advantages. One is it's heavier than air, so you can literally pour the argon into your camera, and it will cause the air and the water vapor to rise up and out, and you have a pure argon atmosphere inside your camera. Or what some people do is they open up their desiccant port, so it's opened outside air. They put their desiccant in the oven to recharge it, And while they're doing that, they put their camera in a bucket and then release argon gas into the bucket, and that will naturally displace the air and fill the camera with argon. Argon's not real expensive. You can buy cans of it off of Amazon. But the advantage to argon over nitrogen has nothing really to do with getting colder per se. It doesn't make it any drier than dry nitrogen. The real advantage is argon has a lower thermal conductivity. And that's what was a surprise to me. I just assumed all gases have about the same thermal conductivity, but that's really not true. And if you look at the table on the right, this is the thermal conductivity at 300 degrees K, 300 K. So around the cool temperature here, and you know, if you use nitrogen, you see it's at 26, whatever wonky units there are. Argon's a little bit lower at 18. You get down to xenon, that's a super good insulator, but xenon has some other issues, like it tends to have a lot of radioactive isotopes, so it would leave hot pixels on your chip. And then helium I didn't realize how terrible it is. It's a very good conductor in a relative sense, so it would make a relatively poor gas to purge with for the kinds of cameras that we have. So you see what's happening here. Nitrogen is inexpensive. It's in the middle of the road for thermal conductivity, and argon is a bit better, maybe 30% better. And that's why some manufacturers, including QSI, recommend argon, but they're pretty clear that it doesn't make it any drier. It's just if you're in a particularly warm environment, that it insulates it a bit better. Therefore, it makes the cooler able to pull the chamber temperature down lower. So yeah, if the camera manufacturer recommends a purge gas, usually it's because, one, they want to have it dry, but often it's to try to improve the thermal conductivity, or decrease it, I should say, make it a better insulator. So for my camera, I have the QSI 683. The desiccant chamber is here up on top. There's 4 hex head screws that hold it in place. You take the screws out, the desiccant cylinder is just below it. It's about 1/3 the size of a AA battery, and you pop that out, you set it on a piece of tin foil, and you put it in the oven at 500 degrees Fahrenheit for 4 to 5 hours, and it'll bake it out. And then as soon as it comes out of the oven, you want to right away put it back in the chamber and tighten the screws down, replacing, mine has a silicone lubricant to help keep that O-ring sealing. So I replaced the silicone on the O-ring, put the desiccant back in there right away, even while it's a little bit warm, and put the plate back on, tighten it down. And now you have a sealed chamber, and that sieve is going to pull the humidity down to about 1%. Topic for another time, but this is also why my effort to make a TeCool Digital SLR was a disaster, at least in Missouri. I really think a TeCool Digital SLR is a neat idea and not very good idea in practice. Neat concept, bad idea in practice. And I think the TeCool Digital SLRs that I've seen on the market are gone now. There was a Canon out there for a while that was offered, and it's not there. And the reason is that if you don't have a sealed chamber and you don't have desiccant, then while you're cooling down the chip, and that TE cooler is exposed because it's not in a chamber, that warm, moist air from the ambient environment is coming into the camera body. Then it's getting cooled, and that water is going to condense because it's going to drop at the TE cooler below the dew point. Then you just have water all over everything, all over the inside of the chamber, the inside of the camera body, on the chip, the electronics, really a mess. So what I see some people do is put a wicking material like a cloth, a cotton material to absorb that moisture and try to wick it out, or fill the chamber with some type of dry nitrogen, or that's the freon that you use to clean electronics. You can blow that in there, try to keep air that just doesn't have the water to begin with. But the air seeps in there. It's just really a mess to fight with. So maybe some other time I'm happy to regale you with my stories of attempting to do this and failing terribly. And one of the reasons is just so messy from a water vapor perspective. So anyway, to kind of sum that up, there's two primary kinds of desiccant: silica gel, which its main value is preventing condensation. It's a great thing to kind of throw in a package with your eyepieces, or under a lens cap, to try to keep condensation while you're transporting or storing your scope, but it's not going to pull a cooled chamber down to a low enough relative humidity to make a difference. Often made from silicon dioxide, so relatively cheap, durable, reusable, and you do that by heating it to 200 degrees Fahrenheit. And the molecular sieve, which is really what enables our cameras to work properly, is functioning by not just preventing condensation, but actually pulling in water in the vapor form. It's actively taking water molecules out of the air to strongly reduce the humidity. They're made from aluminum oxides and some other metal oxide materials. Also very long-term, durable, reusable, and lack chemical reactions. So they're safe in this environment, but require a much more aggressive recharge cycle by heating it to 500 degrees Fahrenheit for 4 hours. I showed that little animal below there. I don't know the name of it, but it's
Horned toad.
What is it?
Horned toad.
Okay. Well, then you'll know better than me. Its skin is made of a desiccating material. It's got real fine pores. So it lives in the desert, but there's sometimes some dew. So it will suck the dew the dew into the fine capillary pores of its skin, and that's how it gets moisture to survive in the desert where it doesn't rain. I think that's it. Just a quick topic, probably stuff you already knew, but it was interesting to me as I learned more about how the camera was operating.